Chapter 2.1, the derivative and tangent line problem, day 2. Let's review the definition of the derivative. The definition of the derivative is f prime of x equals the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. And that finds us a couple of things. One thing it finds us is the slope of the derivative. All right. It also finds us the instantaneous rate of change, which we'll kind of talk about it more in upcoming lessons. Instantaneous rate of change. We also call it the slope of the function. All right, so those are the two main ideas right now behind what is the derivative. It is the slope of the tangent line. Sorry, I misspoke here. And we started finding the slope of the tangent line by first looking at the slope of the secant line, using 2 points on the function, and then letting those 2 points get closer and closer together until they were effectively on top of each other, and then that gave us the slope of the tangent line. All right, let's do a practice problem. Find the derivative of f of x equals 1 over x squared. Well, we will start with our definition of derivative. I'm going to go dy dx form this time. They are interchangeable. One's from Newton, one's from Leibniz. Definition of the derivative, limit, as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. Plug x plus delta x into the function. Well, what we get when we do that is 1 over x plus delta x squared, and then subtract the function, which is 1 over x squared, all over delta x. Now we have a complex fraction. And we've been dealing with these in class extensively throughout the last couple weeks. We need to use a common denominator to get rid of them. So I'm going to multiply top and bottom by x squared and x plus delta x squared. Okay, and when I do that, I'll distribute. When I distribute here, you see the bottom is x plus delta x. So when I distribute here, the x plus delta x will cancel, and I'll just be left with x squared. When I distribute here, the x squareds cancel, top and bottom. Those cancel, and I'm just left with x plus delta x squared. All over, leave the bottom alone, delta x, x squared, x plus delta x squared, and this is still a limit. All right, do a little simplifying. The first simplifying you should do is squaring, then deal with the subtraction in the numerator. I always leave the bottom alone on these complex fractions. So I will square first. So we got x squared minus, and we square that x plus delta x times x plus delta x. You can use your FOIL on that. We get x squared minus 2x delta x. Sorry, plus 2x delta x plus delta x squared. All over our denominator, delta x, x squared, x plus delta x squared. Okay, as we continue. All right, now I'm going to distribute the negative sign in the numerator. This is still the limit. Delta x approaches 0. You got x squared minus 2x delta x minus delta x squared all over our denominator, delta x, x squared, x plus delta x, quantity squared. Now looking at our numerator, we got some simplification we can do. X squared minus x squared cancels. All right? There's an x squared here and an x squared here. Those we can factor out. So let's do that. Let's cancel and factor. Okay, so we'll have delta x factored out. We got negative 2x minus delta x, because we factored one of those out. And on the bottom we got delta x, x squared, and then x plus delta x squared. All right, so taking a look here, we can see we got delta x on top and bottom, so those will cancel off. And now if we do a plug and chug, we let delta x approach 0, it falls off here. So we're just left with 2x on, negative 2x on top. It comes off here, so that's left as x squared. So as delta x approaches 0, what we got, dy dx equals negative 2x over x squared times x squared effectively, which is x to the fourth. Here's a little simplifying we can do. Negative 2 over x to the third. So our derivative of 1 over x squared is negative 2 over x cubed. Now let's try another one. This one's substantially easier. If you think about it, you should be able to get it by looking at it. Because what does the derivative find? It finds the slope of the function. Right? Think about that as we do the problem. So we'll start. I'm going to use f prime notation this time. The limit as delta x approaches 0. We got f of x plus delta x, which is 3 times x plus delta x, plus 2 minus the function, which is 3x plus 2, all over delta x. I think I can get this one done in one page. We'll distribute here. The limit as delta x approaches 0, we got 3x plus 3 delta x plus 2 minus 3x minus 2 all over delta x. All right, so what we got here, if we take a look, 3x and negative 3x will cancel. All right, 2 and negative 2 will cancel, and then we're left with 3 delta x over delta x. Well, since there's a delta x on the top and a delta x on the bottom, those cancel, so what we're left with is 3. And what's the limit of a constant is that constant. So f prime of x is 3, which should make sense. What's the slope of 3x plus 2? It's 3. I told you I could do it in one page. All right, that brings us to an alternate form of a definition, of a derivative, an alternate form of derivative. Now this one is good if you only need the derivative or the slope of the line at a specific point. If we go back to this previous problem, let's go back 2 previous problems. This is the slope of the derivative, or this is the value of the derivative at any point. So if we wanted the value of the derivative at 10, the slope of the function at 10 would be negative 2 over 1,000. If we wanted the value of the derivative at 5, we could plug in 5. Right here, if we wanted the value of the derivative at any function, we could plug in that value. Since it's 3, it's constant. Okay? Here, if you only want the value of the derivative at a specific point, you can use this function. And let c be that point. So if the only difference between this and this definition and the other definition is there's no delta x here. All right? So let's put that on the back burner for now. We'll come back to it. Some theorems, definitions, properties of derivatives. If a function is differentiable, that implies continuity. Meaning, if you found a value of the derivative at a point, it's continuous at that point. So we can go back, look at this one right here. Here's our derivative. What value can we not evaluate the derivative at? 0. because you can't divide by 0. So our original function is discontinuous at 0, which if we look back, it should make sense to us because we can't divide by 0 in the original function either. So if a function is derivative, you can find a derivative, it's continuous at that point. Couple times when the derivative does not exist. Okay, first off, the derivative does not exist if the function is discontinuous. We just talked about that. Right? The function is discontinuous, the derivative does not exist. Number 2, a graph with a sharp turn. Let me show you an example. Here we got a graph. We throw in a sharp turn. Okay. The graph of the derivative does not, or the derivative does not exist at that point. And the reason for that is because the derivative is a limit. And a limit must be the same from left to right. Well, as we approach this function from the left side, we're approaching a very large positive number. As we approach from the right side, we're approaching a very large negative number. So because we're approaching different values, at that one point, the derivative does not exist. And we would just say undefined. And the third time is any graph with a vertical tangent. Okay, an example, y equals x to the 1/3. Looks like this. And this goes back to our limit definitions. This would be a case where we'd say the limit approaches infinity. The graph gets so steep that it's not a number. All right? We can still find values where that happens. We can still, excuse me, approximate derivatives to be infinity. That just means the derivative has a asymptote at that spot. Okay? We're going to pick up this problem tomorrow, but we're going to find the slope of the derivative at that one point using our alternate definition, which is the limit as x approaches not 0, but c. So it's f prime of c is the limit as x approaches c of f of x minus f of c all over x minus c. This one is a nice one to know, but the other definition with the delta x is a must know.